Did I start? Yeah, we already start setting people. Hello, everyone, and welcome to another webinar from the AVSO. We have at least 10 more minutes until we get started, but please feel free to introduce yourself on the chat. Let us know where you're from, how the weather is, and we're going to be with you shortly. Thank you.
Oh, there's 19 people so far. Well, 20, well, including us, I assume. So, yeah.
Oh, yeah.
Just watch the little number go up.
Well, that's fun.
Yeah. Hello, Nebraska and Illinois. It's actually quite pretty here in Massachusetts.
Oh, did you hear, Stella? They're saying that the leaf peeping season is going to be longer this year, earlier and longer because of the drought.
Oh, that's going to be interesting.
Now, the colors might not be as great, but it supposedly, some of the trees are already starting to turn.
Yeah, I've seen a few already.
Yeah.
Same here. Oh, we're looking forward to it. It's my favorite season, actually.
Yeah.
Yeah.
Just don't like raking.
Hi, Arizona. No, no one likes raking. So if you check at the chat, you'll see people coming through, introducing themselves.
It's great.
Cool. So how was the sun this morning? Has anyone checked?
Yeah, John checked. Nothing.
Blank.
Yep. Dead.
Blank.
Blank.
Blank. And we had beautiful, excellent transparency today.
Oh, yeah.
Yeah, cold front came through, so it's nice and crisp and clean and beautiful.
Yeah.
It's beautiful here. We're for a great weekend. So we have people coming from Maryland, the Philippines, Venezuela, Maine. Welcome, friends. What time is in the Philippines?
12 hours.
Is it?
From now.
Wow.
Something like that. More or less.
Cool.
Yep, 1:52. That's 12 hours.
Wow. Thank you so much for joining us.
Yeah.
Really cool to have you online.
Excellent.
That's fantastic.
Caracas, Venezuela. How is Venezuela today? It must be sunny and beautiful. It's always sunny and beautiful. Yeah. We still have 10 minutes to go. So I guess I'm cheating because the image that I have is an X-rays of some sort. X-ray image alpha.
Okay.
Yeah, I know. Hello, Illinois. Good afternoon, Germany. Good evening, actually. It's evening right now there, right?
Yeah. Gary Walker, hi.
We have people coming in. So anyone has plans for Labor Day? It's Labor Day in the US.
Labor Day, Canada too.
Labor Day in
Oh,
Canada
well,
as
there we go.
well. Awesome.
Yeah, not too much. Well, lots of yard work.
Yeah, that kind of thing. Harvest tomatoes.
Oh, tomatoes. Yes. We have so many tomatoes.
I think it was a good year for them.
I think so. 2 days ago, they were green.
Wow.
Yesterday, we went out to see what was ripe, and there were so many.
Gosh.
What type of tomatoes do you have?
We've planted over 36 varieties.
Wow.
Oh my goodness.
Yeah, well, we're seed savers, so we collect heirloom seeds.
Oh
Oh,
wow.
cool.
So there's it's going to be a lot of work.
Yeah.
Wow. It
I
must be
just,
very rewarding.
Yeah, it is. It's fun. It's
Yeah.
just yeah, it's just interesting. From a little seed, you can get that plant and all that, all those tomatoes.
yeah, that is amazing.
That's
Yeah.
that's
We
something.
just, when I get tired of making tomato sauce, then we just chop them up, wash them, chop them up, and freeze them. Put
Oh
them in
yeah,
Ziploc bags, and then you can dig them out next winter and make
yeah,
stuff. It's nice.
yeah. I usually do up stewed tomatoes and freeze them. This year, I'm going to try dehydrating some and see how that
Oh,
works.
ooh, that'd be neat.
Yeah,
Nice.
we'll see. It's
I'm
going to
looking
take
at
20 to 24 hours to dehydrate them. I
Oh,
don't
Well,
know.
there's a lot of water in those suckers, you know?
yes,
Yeah.
there is. Wow.
And these are, they just, from the dehydrating book, it's like use the small grape-sized ones, not the big ones, just the
Oh,
small
yeah,
ones.
there you
So
go.
we'll see what happens.
Do you have a dehydrator machine, or do you do it in the oven?
Oh no, I have a dehydrator.
Oh, that's good. Yeah.
Yeah. So I can do some herbs with it, and I'm going to dehydrate the garlic this year so we
Nice.
can create
Wow.
powder. Yeah.
Cool.
Yeah.
So while we're chatting, we have people coming in, logging on the webinar. So for those who just arrived, welcome. So those who come, just introduce yourself in the chat. Let us know where you're from. So greetings to Peru and France, California, Cape Cod, Germany, Illinois, the Philippines, Venezuela, Maine. It's wonderful to see people coming from all over the world. We have more than 70 participants right now. So it's really, really cool. Hello, Cape Town. Ohio, Albuquerque. We have 5 more minutes to go until we get started.
I'm seeing a lot of familiar names in the attendee list too. Welcome,
Yeah, it's
everyone.
really cool.
Al Takeda, how are you? Hello, Al.
I'm waving from the other side of Cambridge, Massachusetts. Hello, UK, Vermont, New Mexico, London, Connecticut. Oh, wonderful. Indiana. Hi, Hoosiers, fellow Hoosiers. I am a Hoosier girl. Come on. I spent 6 years in Indiana. I got my PhD from there. So pride and joy. Hello, Argentina.
Bert, is my volume better? Bert said I was loud.
Oh, you're doing well. Bert is not online today.
No, another Bert from the
Another
chat.
Bert.
Another bird. Oh, sorry.
Okay.
Aha.
He said better.
Nice. Yosemite. How's it in Yosemite right now? How's the weather there? Vermont, New York, California. Ooh, 98. Okay.
Gosh.
I'll come visit you next spring. Oh. Wonderful. New Hampshire. It's so cool to just see everybody coming together.
Yeah.
The Barbados. Oh my gosh, I'm so jealous now.
Nice.
London. Hi, Jay. Good to see you again. Chicago, Canada. Cool. Hello, Tucson.
Well, we've broken 100, so.
That's great.
Ooh, hola, Chile. Hola, Argentina. Buen día. I need to practice my Spanish a little bit more. Hello, Spain. Wonderful. It's so refreshing to see people from our community internationally coming and joining us.
Yeah.
Wow. Hello, South Africa, Spain, Iowa, United Kingdom. Cool.
Aldrin, how are you doing?
So we're gonna give a couple of more minutes. So everybody's settled with their tea or coffee and then get started. Hello, India. Good to see you guys. This is the silence before we get started and all the excitement
Well, we're
starts.
all
It's kind of
mesmerized by the names.
I know. We've been discussing on whether we should put some music for that interval. People have been proposing different kind of pieces. Any ideas? Any preferences? Like the one from Star Wars, for example.
Something about the sun.
The sun.
Rodney Aldrin calls you Sir Rodney.
Yeah.
Yeah, not necessarily. You're right.
That's
We
cute.
don't need music.
He was from the Philippines and then he went to the UAE.
Oh, wow.
Wonderful.
He
That's great.
submits sunspot data. Oh, John Ewan. Whoa, how are you?
Hey, Frank's here. Hi, Frank.
Hey, Frank.
Hi,
Hey,
Frank.
Frank.
Shout out to Frank.
Yep.
Awesome. So Berkeley, California. Oh, wonderful. So as people come, we have more than 120 attendees. So it's officially a party. Good morning, good afternoon, good evening, everyone. My name is Stella Kafka, and I am the Executive Director of the AAVSO, and it is a pleasure to introduce another webinar of our series. Today, I am joined by Chris Larson, Kim Hay, Rodney Howe, and Sarah Beck, and who are all members of our solar section, and we will be discussing our own star, the sun, and the AVSO solar program. At this point, I would like to acknowledge and thank our supporters, the Boyce Research Initiative and Education Foundation, which provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools to learn how to perform observations, conduct research, and publish the results in scientific journals such as the Journal of the AVSO. They have been a partner and close friend of the AVSO for years, and they are supporting this webinar. And also ATI Cameras, manufacturing a diverse range of quality astrophotography cameras and accessories, along with a range of free software to help you maximize the output of your equipment. And for more information, please visit their webpage. They have lots of really very interesting offers there for our community. At this point, I would like to start with a couple of housekeeping items. There are two buttons at the bottom of your screen on Zoom. The one is the chat where you're introducing yourself right now. The second one has a Q&A, question and answer on it. Please use that to ask any questions you want answered by our speakers. We will address all questions after the presentations, but please feel free to ask at any time. And if we don't reach them, please reach out to our experts through our forums, and we can continue the discussion there. Also, in your low left-hand side, there is an icon that looks like a microphone. If you click there, there's a drop-down menu that provides selections which control your audio settings. If you have any issues with your audio, please look at these relevant settings. We cannot help you fix from here. So at this point, I'm going to stop sharing my screen and leave it to Christine Larsen, who's going to get us started.
Okay. And now
Throw you
I'm
first.
going to start sharing my screen.
Awesome.
And we'll just make sure that it's all working. Oh, back up. All right. So how is that looking, Stella?
Awesome. Thank you.
Okay, great. Well, good. Fill in the blank, whatever time of day it is. Good day, evening, whatever to all of you. And of course, day and evening are defined by our featured astronomical object in this week's webinar, the sun. So I'm going to be taking the lead introducing visual solar observing and the AAVSO solar section. The solar section is a different kind of section from the other AAVSO sections because we only look at one object and we do our work during the day. I thought I'd start with a little bit of an overview of the structure of the sun because I'm not going to make any assumptions on what people may or may not know about our star. Our sun is a very Joe average middle-aged star for which we're incredibly thermoful. It has an outside set of layers and an inside set of layers. At the heart of the sun, we have the central engine, the thermonuclear core, about 15 million degrees Kelvin, which is busily every day converting hydrogen into helium, and through E equals mc squared, a little bit of excess matter is being converted into energy. And the energy is emitted as high energy photons, and they have to get from the center of the sun to the surface of the sun. And it's sort of like a giant pinball game because those photons, those particles of light, bounce around and bounce off of all of the electrons and eventually make it their way out towards the surface of the sun. So outside the thermonuclear core, we have a region of the sun where the photons are bouncing around and interacting and trying to get out. That's called the radiative or radiation zone. And then we have a very important transition inside the sun, more on this later, called the interface layer, where the energy, instead of being transmitted by these pinballing photons, we talk about the sun boiling or convecting. And so if you've looked at a pot of boiling water, you know that when it comes to a rolling boil, you see literally bubbles of material convecting. And so heat is being transferred through the actual up and down motion of this hot gas. Now, the top of this convective or convection zone is the so-called visible surface of the sun. I always use scary air quotes because the sun is not a solid body, but it is an opaque gas that you cannot see into. So that visible surface, if you go out and look at the sun, which you all never do because you know you're not supposed to go out and just look at the sun with your eye, but that visible globe you see in the sky, that is the top of the convective zone, and that's a layer that we call the photosphere. Now, there are two other outer layers beyond that visible surface of the sun. We have the lower atmosphere, which we call the chromosphere, chromo like as in color, and the corona, the crown, the crowning glory of the sun. So we normally see the photosphere on a given day, and in fact, for most of our solar observers, that's the part of the sun that they're actually observing, is the photosphere. Now you can see the chromosphere if you have a hydrogen alpha filter. The chromosphere gives off a great deal of its light at one particular wavelength, which is due to hydrogen, the hydrogen alpha wavelength. And if you have a hydrogen alpha filter, you can see the chromosphere rather than the very bright photosphere. But if you don't want a special filter, you can follow the next total solar eclipse. I know there's a lot of eclipse junkies here on this call, myself included. And when the moon passes in front of the sun and blocks out the photosphere, we can actually see the chromosphere and the corona for free. But the photosphere is going to be the star of the show today, no pun intended, for the solar observing. And since it is the top of this boiling zone of the sun, if you look at the photosphere in high detail, you will indeed see these boiling up and down motion of blobs of gas. And that's something that we call granulation. I usually describe it to my students as if you had old-fashioned oatmeal boiling on the stove and threw in some yellow food, food poisoning, some yellow food coloring. Now, what do you actually see if you safely, and we'll get to the safely part in a little while, when you safely look at the photosphere of the sun? You will see that there are features that change on an hourly, daily, weekly, monthly, yearly basis. And that's really why we do what we do here in the solar section. We are looking for these changes that are always occurring in the visible surface of the sun in the photosphere. And the two main types of features that we're looking at are sunspots, which were originally called maculae, and these are dark appearing areas. The key word here is appearing, right? They are not black spots on the sun. They just sort of look like that. Then you also have sort of the opposite effect. You have brighter appearing areas, which are called faculae. So if you look at very old historical records, you will see maculae and faculae being discussed. And the faculae are harder to see, those darker appearing areas, because of contrast. Those sunspots are easier to see against the disk of the photosphere. To see the faculae, you really have to use the trick of looking near the edge of the sun. The edge of the sun is what we call the limb, and you actually are looking through more layers of gas in the photosphere there, and so you actually get a little bit of a darkening, a dimming of the edge of the photosphere, and that's what we call limb darkening, and that little bit of extra contrast can really help to bring out the faculae. And the reason why we're interested in faculae, especially now when there are so few sunspots, is because sunspots are often born in areas of faculae. So if there's no sunspots visible today, for example, but we see a beautiful region of faculae along the limb, we're going to keep an eye on that area because sunspots may pop up in the next couple of days. Sunspots have an interesting structure. And here are terms that you might be familiar with for eclipses: umbra and penumbra. In terms of an eclipse, the umbra is the central darker area, right? That's where the total eclipse is. And a penumbra is the outer, almost dark area. And so we use the same terms to denote sort of dark and almost dark to talk about the structure of a sunspot group. These are incredibly large sunspot groups. I'll actually give you some scale in some of the pictures coming up, and you might be totally shocked to think about how large some of these sunspot groups actually are. But if we zoom in, again, you can see the granulation in this right-hand picture, and then you can see that area in the center looks much darker than the area around it. And again, the umbra and the penumbra. Now, sunspots are just the most obvious of a wide variety of activity that our sun engages in. And because they're so obvious, we've been observing them for a very long time. We've been monitoring them consistently since the time of Galileo, although we do have sunspot records going back to ancient China, ancient Japan, ancient Korea. We have Mayan. So it's not like Galileo was the first human being to ever see a sunspot. We know that's not true. But since the time of Galileo, since the early 1600s, we have been consistently trying to monitor sunspot activity and try to figure things out about our sun. So I've been using the word that sunspots are darker appearing areas. They appear dark because they're about 1500 degrees Kelvin cooler than the surrounding photosphere. If you could surgically remove a sunspot with a pair of very large tweezers and hold it out, you would actually see that it does emit light. it would look sort of like the dying embers of a campfire. And the really cool thing about sunspots is their changeability. They grow and fade over time scales from hours to weeks. Occasionally, you get a really big, nasty sunspot group that will last for a couple of months. And on this particular picture in the lower right, you see the scale, you see our planet Earth in comparison to these sunspot groups. There are sunspot groups that are larger than the planet Jupiter. And Jupiter, remember, is about 11 times the diameter of the Earth. When you start getting sunspot groups that are the size of Jupiter, if you still have your eclipse glasses from one of your eclipse trips, you can actually see those very large sunspot groups safely with your eclipse glasses. Now, what are sunspots? If you look at an astronomy textbook, you will often see terms like sunspots are magnetic storms on the sun. Well, what does that really mean? Sunspots are areas where the magnetic field strength is between 10 to 40 times stronger than normal. And so the question is, well, how do we know that? We know that through something called the Zeeman effect. And so here's a little bit of physics thrown in for today. So the Zeeman effect, here we have taking a slice through the sunspot and looking at the spectrum at various places along the photosphere. And in the area where the sunspot is, the spectral lines, if you notice, this one spectral line splits into 3 lines. That's the Zeeman effect. So the Zeeman effect happens when you place atoms in an external magnetic field. And because electrons have negative charges, they are going to interact with a magnetic field. This external magnetic field exerts a torque on the electrons, and it actually changes their energy. And so way back from your high school chemistry, you might remember those energy levels you had to memorize: 1s2, 2s2, 2p6, 3s2. I'm sorry if I've brought back any bad memories for anyone. But you see these, the 2p, these levels, they all are usually drawn as being like of the same energy. Well, they are until you put it in an external magnetic field. And then there are slight differences in energy, and that's that tripling of that spectral line that I showed you in the last picture. And so and the amount of that tripling, that is how we know how strong the magnetic field is in the sunspot areas. One really cool thing about sunspot groups, and every sunspot group has its own distinct personality, is that very often they come in what we call bipolar groups. Sunspot groups can be incredibly messy, but if you look carefully, there's usually sort of 2 larger members, or maybe one member that's larger and a smaller member. That's what we mean by bipolar, okay? And then there can be other little spots around them. And so the question is, why do they typically occur in these bipolar groups? Well, it's physics. And so the sun has a very intense magnetic field. And what happens is that at the location of a sunspot group, the magnetic field lines actually exit the sun, loop around, and come back down into the photosphere. So you can think of the 2 members of that bipolar group as sort of an exit wound and an entrance wound in the photosphere, where the magnetic field lines pop out and then pop back in. And these looping of the magnetic field lines actually blocks the convection of that hot gas. And because in that area where the field lines are popping out, looping around and coming back in, because it's actually stopping the convection, you're preventing the hotter gas from rising. Therefore, you're making the area surrounding the sunspot cooler, and hence it gives off light and looks darker. One of the really cool things that was discovered very early on in terms of our observations of the sun is that you can actually monitor the rotation of the sun by watching sunspots. Because an individual sunspot or sunspot group can last for weeks, you can actually watch it appear to move across the sun. Now, it's not that the sunspots are getting up and running across the sun. That would be kind of cool, but kind of scary. What's actually happening is that the sun is rotating and it's carrying the sunspot groups with it. And so here we again have sort of a time lapse showing you the rotation of the sun by showing you the motion of the sunspot group. And again, here for comparison, here's the Earth, and here we have this ginormous sunspot group there. But there's something really cool about the motion of the sunspots. If you watch the rotation of the sun, as measured by the movement of these sunspot groups, you will find that spots near the equator move faster than those at the higher latitudes. The sun actually spins faster at the equator and slower at the poles. This is something called differential rotation. And the reason why the sun is allowed to do this is because it is not a solid body. And it turns out that it's not all of the sun that engages in this weird rotation. That's going to be a very important point. But before I plunge into that physics, I want to just complete the thought of why we're observing these spots to begin with. As I said, the individual spots are born and die over time frames in hours, days, weeks, on the longest scales, months, but they're always changing. And it turns out that if you monitor the amount of sunspot activity, you end up with a cycle of activity level. There are times when there's much sunspot activity, and there are times when there's very little sunspot activity. And so we call this the sunspot cycle. On average, the time between one maximum and the next is around 11 years. It can be as low as 7 years. It can be as high as 17 years. So when you ask solar scientists, when is the next maximum, they can't really tell you exactly when the next maximum is. They have to wait until it occurs, and they look back and go, oh, that was the maximum. Now, there are some patterns that we observe besides the fact that there is this cyclic cycle of around 11 years. And some of these rules are sort of bundled together in what's called Hale's polarity law. So remember I talked about this bipolar sunspot group as a place where the magnetic field lines pop up, loop around, and go back in. Think of it like the feet of a horseshoe magnet, right? If you have a horseshoe magnet, one of the feet of the horseshoe magnet has a north polarity, and the other foot of the horseshoe magnet has a north and a south magnetic polarity. Similarly, in one of these bipolar sunspot groups, one of those main spots has a northern magnetic polarity, and the other has a south magnetic polarity. And if you look at sunspot groups in the northern and southern hemisphere of the sun, above and below the equator, if you will, you'll notice in my picture, if we say that red represents north magnetic polarity and blue is south magnetic polarity, you'll notice that the polarity of the leading sunspot, the sunspot in front, if we're talking about the way the sun rotates, that the polarity is different in the northern and southern hemisphere, right? But at the end of that 11-year cycle, when the new 11-year cycle starts, what happens is that the sunspots of the new cycle have a switched polarity. So you will sometimes hear about a 22-year solar cycle to take into account that the overall magnetic polarity of the sun changes from one cycle to the next. And so it takes 22 years or 2 cycles to go back to the way it was. And from one of these 11-year cycles to the next, the polarity of the leading sunspot in each group in the northern and southern hemisphere will switch. That is interesting and important because it allows us to identify the spots of the dying cycle as opposed to the spots of the new cycle. And that's how we're going to know when we go out of solar minimum, More on that in a couple of minutes. Now also notice in this picture that the sunspot groups are sort of parallel to the equator, but there's a little bit of a tilt in them towards the equator, and that's something called Joy's law. So as I mentioned, I said that we can distinguish between the last sunspots of the old cycle and the first sunspots of the new cycle because they have a switched polarity in terms of the north-south dichotomy of in the northern and southern hemisphere, right? So here we have, this is what's called the butterfly diagram. Here we have all of the sunspots plotted more or less from 1996 through about, let's say we'll stop this cycle here, around 2009, 2010. Over the course of the sunspot cycle, the location of the sunspots on the sun starts to migrate. So when the new cycle starts, the new sunspots of the new cycle tend to be born at higher latitudes. And then as the years go by, you see spots more commonly at the mid-latitudes. And then towards the end of that cycle, the spots are more common near the equator. So right now we have been in a solar minimum. So the sunspots of the old cycle, what spots there have been, are closer to the equator. But simultaneously, we're all celebrating because we have seen the awakening of the sun. We know that cycle 25 has started because we have seen high latitude sunspots of a swapped or opposite magnetic polarity. So we know that we will eventually be coming out of minimum because we have seen some of the spots of the next cycle. Now, where does all this stuff come from? If I put all this sort of together in one slide, okay, and this is as sort of technical as I'm really going to get here. This is something called the Babcock-Leighton dynamo model. Remember that the sun has a differential rotation. Remember that different parts of the sun are rotating at different speeds. And so what happens is that at the beginning of the sunspot cycle, you have a essentially perfectly dipole magnetic field. A north magnetic pole, a south magnetic pole, and the magnetic field lines go from north to south magnetic pole. But because of the differential rotation, those magnetic field lines get twisted and start lapping each other. And that's something called the omega effect. And so you go from being a dipole to being sort of a wrapped around the equator or a toroidal field. At the same time, you also have the convection in the photosphere. And so what you get is an up and down twisting of the magnetic field lines, right? The little magnetic field popping out of the photosphere and popping back in. So you end up with these magnetic loops. And over time, these magnetic loops are all aligning each other and they will reestablish the dipole field again. And that's called the alpha effect. And how long it takes to go from dipole to toroidal and then the twisting back to the alpha effect, back to the dipole again, that's 11 years. But again, you'll notice from the first picture to the last picture, you notice how the directions of the arrows have swapped. Because again, at the end of one 11-year period, we have the opposite magnetic polarity. So a question might be, where does the magnetic field of the sun comes from? It comes from electric currents deep within the sun, the circulation of hot ionized gas, i.e. electrons, and it happens at that interface layer that I mentioned at the beginning, the place where energy transfer goes from the pinball effect of light, of photons, into the convection. And so this diagram shows you distance from the center of the sun. So this would be the photosphere, this would be the surface. This is about halfway from the center of the sun. And this has to do with the actual angular velocity at different latitudes. And you'll see that at about 65% out from the center of the sun, you start getting this differential rotation by latitude. And that's where the magnetic field is generated, a place within the sun called the tachocline. So I don't explain all those details to my students. If someone asks you what causes the sunspot cycle and they want a really quick and dirty answer, just say that because different parts of the sun spin at different speeds, the magnetic field lines get all tangled up, sort of like a kitten playing with a ball of yarn. And the magnetic field lines become so hopelessly tangled that they actually snap and recombine, and that leads to activities such as solar flares. And again, here we have the approximate size of the Earth compared to the solar flare. And solar flares are often connected with what we call coronal mass ejections, which are mostly responsible for geomagnetic storms on the Earth. And these are huge bubbles of gas threaded with magnetic field lines that are ejected from the sun, which is great if you like looking at northern lights, not so great if you like your cell phone service and things like that. Now, one thing about the sun is that you might be saying to yourself, well, this is all well and good, but this is the American Association of Variable Star Observers. How is the sun a variable star? Well, the answer is that the sun's brightness actually changes over the solar cycle, but it doesn't change the way that you would think. Most people would think, and I think it's probably makes common sense, that if there's more sunspots, and if sunspots are cooler and darker, that more sunspots should make the sun dimmer, right? So you might think that during sunspot maximum, when there's more sunspots, that the sun is dimmer. It's actually not. Because remember that there are those brighter, hotter appearing areas, the faculae, that are associated with the birth of sunspots. And it turns out that the faculae overcompensate for the sunspots. So the sun is actually a little teeny tiny bit brighter during sunspot maximum than it is during sunspot minimum. And if you want to know what I mean by a little teeny tiny bit, look at the scale of the y-axis of this graph. You know, we're talking about very, very tiny, couple tenths of a %. So our sun is considered a rotational variable, specifically a spotted star. It has two periodicities. It has a periodicity of about a month because of the rotation. And we also have a roughly 11-year period because of the number of spots that change. And to give you a comparison, here is another rotational spotted variable, the star 40 Eridani, which is a K-type star. It is orange. It's a little cooler than our sun. You may know this star as supposedly the home star of the planet Vulcan in Star Trek. Now, there have been, and Rodney can answer more questions about this in the Q&A if you're interested, but there's been some people who have claimed that sunspots are responsible for global climate change. And so solar scientists have looked at the sunspot cycle over the period of time where we have records going back from Galileo, and we have found that there has been no weird change in the sun's behavior over the last 2 centuries. The sun is not responsible for global climate change. So that is background of the sun. The nuts and bolts of how do you observe the sun? It's actually pretty simple. It's the safety part that's important. So there are 2 ways that you observe the sun. You can either safely project the image on a screen, or you can use a filter. And it's very important that the filter be what we call an aperture filter. It goes on the front of the telescope. It prevents the light from entering the telescope in the first place. There were back, I believe in the 70s, there were so-called eyepiece filters that were sold with some very cheap telescopes. And these eyepiece filters that went on the eyepiece of the telescope failed, leading to people losing their eyesight. So you must block, if you're going to be directly observing the sun, in other words, not projecting it, you need to make sure that you are preventing the light from entering in the first place, that you are using a solar filter that has been sold to you by a reputable dealer. There are many different kinds that you can buy. Some of them are metal alloy evaporated on glass, and some of them are more of a flexible material. Also, be very careful with any other accoutrements you have hanging off the side of your telescope. You do not need a finder scope to find the sun. In order to find the sun, what you need to do is just minimize the shadow of the sun on the ground, minimize the shadow of your telescope on the ground. So the scope that I use to observe the sun, I actually have permanently removed the finder scope. I don't even know where it is anymore. That way, make it idiot-proof for myself and anybody else I'm observing with. So we have about 60 observers worldwide providing counts to our solar section, and it's split about half and half in terms of projection and direct observing. So what we want to do is we want to look at the areas of activity. And so the areas of activity, again, I've already given you sort of the punchline. An area of activity could be a bipolar group, or it could be a very messy group. It's an area of unified magnetic activity. And so we measure what we call the groups, and then within the groups, we count the number of individual spots. So you have to identify how many groups there are and how many individual spots there are in all of those groups. And since each group is a different area of activity, it's more important, and it's given a weight factor of 10. So the so-called Wolf number is 10 times the number of groups plus the overall total number of spots. Now the Wolf number jumps from 0 to 11. There's nothing in between, because this one group, this one spot by itself is also a group. So that would contribute 10 times 1 is 1, plus 1 is 11. So who was Wolf? Rudolf Wolf from the Zurich Observatory. He was a standard observer. He observed the sun on every clear day he could, and he had his own scale of measuring the sunspots. He was succeeded by a gentleman named Wolfer, and at Zurich, they became known as the standard of solar observing. And so the relative sunspot number is found by multiplying your Wolf number, your 10G plus S, by some factor that corresponds to the fact that you're not Wolf. Okay, it's a relative sunspot number. And so you'll sometimes see here that the relative sunspot number is some coefficient K times 10G plus S. The AAVSO solar section came about by necessity. In World War II, there was a disruption in the flow of solar observations from the Zurich Observatory, and solar flares disrupted submarine communications, so this was a matter of national security. So the recorder of the AAVSO, Leon Campbell, suggested to one of the observers that he propose an AAVSO solar section that was actually started in 1944, and by the following year had about 53 members. And their primary job was to produce the sunspot counts for the National Bureau of Standards. And from that, they computed not the Zurich relative sunspot number, but the American relative sunspot number. Now, the AAVSO didn't have one standard observer like Wolf or Wolfer. They were taking observations from many, many people. So Alan Shapley, the son of the Harvard College Observatory director Harlow Shapley, used statistics to try to figure out how we could put together in a trustworthy way the observations of many different observers. And the answer is to use, again, this weighted factor, this K factor, which we use to calibrate the visual acuity and the instrumentation and the observing site of an observer. And it's not a static thing, because as people improve as observers, their K factors can change. And we always at the AAVSO want to make sure that our statistics are always the best. So the K factors are sometimes recalibrated just to make sure that there hasn't been any creep in the statistics. And to become a trustworthy solar observer, there really is no substitute for experience. Because when the sun becomes very crowded during solar maximum, it can be sometimes a little difficult to distinguish one group from another group because the groups might almost overlap each other. And there are different shapes of groups and flavors of groups. And this is something that we call the Zurich system. What does a newborn sunspot group look as compared to an older sunspot group? Well, how do we really know that the American relative sunspot number is standardized if there's no standard observer? Well, we've actually had at least three modern observers who pretty much can almost be called that. Herbert Luft was observing from 1924 to 1986, and his data has been digitized by the AAVSO. This is the data from one individual. Is that just absolutely gorgeous, gorgeous data? Those are his group numbers from 1924 to 1986. Similarly, Tommy Craig, who some of us still remember, quite a gentleman, quite a character. He also, for many, many years, observed the sun methodically, carefully. And his observations have also been digitized. And there's his absolutely gorgeous data. And more recently, we have a gentleman from Japan who also has been giving us the data. The data that we actually include in our database has to be daily data, and we are getting his monthly data. So his data is not directly in the database, but if we look at his contribution and look at it compared to the other gentleman, and again, there's overlap in the years that they were observing, once again, absolutely gorgeous data. So we can create a time series of plots that overlap in time from these absolutely master craftsman solar observers, and we can check it against the calibration. So we are very, very convinced that the AAVSO solar data is high quality. And if you're interested in digitizing data, there's a lot of AAVSO data that still needs to be digitized. And again, why do we want to do this? Because we want to understand why it's not exactly an 11-year cycle and why some cycles have higher maxima and lower minima than others. So if you're interested in becoming one of us, the Solar Observing Guide is available for free on the AAVSO website. It has been translated into numerous languages. And as you improve as an observer, you can compare your observations to the observations of other people. This was one of my early observations back from, I think, 1990, and I tended to overcount groups. And so I went back and I learned, I improved as a solar observer. And this is the best time of all to join us because now we are coming out of solar minimum. We are going from cycle 24 to 25. So this is the perfect time. You can get in on the ground floor. Don't miss cycle 25 coming to a solar telescope near you right now. And with that, I'm going to stop sharing my screen and turn it back over to Stella.
So let's get started with our next speaker, who is Rodney Howe, and he's going to talk about BLF radios and collecting data for the AAVSO Solar Bulletin. I am going to be progressing. Can you see my screen?
Yeah.
Right. I'm going to be progressing your slides, Rodney. So take it from here.
Okay. I want to note the friends and the mentors that I've had, like Joseph DeVerde and Doug Welch, and Nathan Town. These folks are mentors to me. And then I, in turn, mentor Marjan and Susan Oatney and other AAVSO observers who have built their radios or are presently submitting their data on a monthly basis. So next. This is how we start. building radios for our flare patrol. Up there on the top, you can say, join the flare patrol. Here's Marjan. She's building an antenna with an octagon antenna, and she's going to wrap about 100 meters of wire around that, and that's going to be a loop antenna. It's not difficult. Let's just say that you have to have some desire to construct these antennas, because no matter what radio you build, it's really the antenna that's going to receive the signal from the naval transmitters. Next. Here's Casper Hosfield. He was the solar section SID analyst up till 2002. He's an old radio builder, and here he is building radios, and he's on our website, on the AVSO website. He has instructions on how to build gyrators and how to build the antennas. If you go to the AVSO website, look for SID equipment, and most of it's going to be Casper's radios and his antennas. Next. If you're building your radio, here's a workbench. You can see oscilloscopes, and you can see power supplies, and you'll have to be a good soldering person, and you have to know what capacitors are and resistors are, and you have to know what transformers are, and the red and black power supply cables, the antenna curling along the bottom here. So this is one way that you can get involved in recording data from the sun. I'll talk about that in a little bit. Next, here's a radio set up with what they call an up converter. The radio waves that we're receiving from the naval transmitters are very long wavelengths, very low frequency. Some of the wavelengths are kilometers long, and most radios that you buy, you can't receive the VLF. So they have that little box up there is a VLF converter. It converts the very long wavelengths to megahertz, in this case to 4 megahertz. And now you can use your ham radio to look at 4 megahertz, and then you can track the audio. And then with the audio, you can hook up a digital converter or a sound card. Next. But this is the modern bench. Here's new radio builder's bench. You can see up in the upper left, there's a hexagon loop with 24 braided copper bands, about 100 meters of wire. And then it leads right to the sound card. That black box there is the sound card. It's external. And then from a USB port, you go right into the little computer, which is a Pi. And on the right, you can see the setup where you've got the Pi 0 little computer, the green thing right there. That's a whole computer running Linux operating system. And then the sound card goes into it. And then from the Raspberry Pi, you go to the TV screen and you can see the graph there. That's a nighttime and daytime 24-hour graph. So this little Pi 0 will record data day after day after day. You don't have to do anything except look at the graphs. Next. So sound card software. If you look down here in the lower left, you can see its kilohertz is 96 kilohertz for the sound card. So it's got to be a high definition sound card. Then you've got the 24 bits. In other words, if you have less than 24 bits, then the modern software isn't really going to capture the signal. So it's a good idea to get a good external sound card. Okay, next. This is the frequency of the sound card. This is the spectrum. You can see if the antenna, like that hexagon antenna with 24 loops, resonates around 23 kilohertz. But over on the right, you can see 3 peaks. And the left peak is 24 kilohertz, and that's from Cutler, Maine. And the next 24.8 kilohertz, that's from Jim Creek in Washington state. And then the right peak is Lemoore, North Dakota. Right, there you go. No, you can go back down there. So here you can see in the blue spots right on the American side, you have Cutler, Maine, and then you have Lemoore, North Dakota in the middle of this country, and then you have Jim Creek on the left. And then in Hawaii, you have a blue spot, and that's NPM. That's the call sign. And then way down on the left in Australia, we have an American transmitter down there, NWC. And that's at 19.8 kilohertz. That's the lowest signal, longest wavelength. But you also have all the different countries in Europe. Almost every country almost has a transmitter. Italy, UK, France, Turkey, they all have their own transmitters transmitting these very long wavelengths to submarines under the water. The submarines, they don't have to surface. They can lie about 20 meters under the water, and these transmitters will transmit to all the ocean's submarines. Okay, next. Here's an example of Cutler, Maine. This transmitter is huge. It's got 2 spider webs, I call them, and these cables are thousands of feet. And they have a nuclear reactor on this one to generate the power in megawatts, millions of watts of energy, just pounding the surface of the earth and then going up to the ionosphere, reflecting off, and then going into the ocean. Next. This is the one in Japan. This is Haiku antenna, and you can see the mountain ranges around it. And you can see that there's like 7,200 feet of wire. We're talking over a mile, and it's 1,500 feet tall from the base where the transmitter building is. And their wires are spaced 100, 400, 100. And this transmitter is JJI, and it transmits at about 40 kilohertz. Next. This one is Jim Creek in Washington. And again, you can see it's from mountain to mountain range. And it's got the insulators in the bus and the transmitting building, counterweights to keep the wires taut. The wires are 8,700 feet at the start and almost a mile in length at the end and a mile long. These are huge transmitters. This one transmits over the Pacific Ocean to Hawaii, and Hawaii picks it up. Next one. Here's the one in Hawaii. Again, thousands of feet of wire on 600-foot towers sitting in the middle of a mountainside in Oahu. Next. Okay, this is what's happening. The sun during the daytime separates the ionosphere, and you can see you've got F2, F1, E, and D layers. When the solar flare penetrates down to the D layer, we're going to get a SID. We're going to get a sudden ionospheric disturbance. That's what it's called. During the nighttime, all these layers coalesce, and there is no real mirror is what we're looking for. The mirror comes about because of the ultraviolet light impacting the D layer. And if there's a flare, the flare will put out X-rays, and the X-rays will reionize the D layer and cause massive disturbances in the communications for the submarines. So that's what a SID emit. Next. Here's the propagation through a D layer. Okay, so the ionized layer would be a D layer. It turns out to be like a mirror. And the transmitter pushes out up to the D layer, reflects back to the Earth, and then like in point A, the skip distance goes from the Earth back up to the ionosphere and down. And these are like 1,000 kilometers in wavelengths. And then on the Earth, you might have a submarine under the water, and the VLF frequency will penetrate down to about 20 meters. Submarine doesn't have to surface during the day. Next. Here we go. We have an impact coming in. It rings the ionosphere like a bell. And you can see the red side is Hawaii, then Jim Creek up there. Then this is Fort Collins, Colorado, where it crosses. There's a transmitter in Puerto Rico. We don't use it very much, but it's there. And then the one from Cutler, Maine. So this is actually talking about a magnetar during the nighttime when we would receive a signal from something, maybe from intergalactic. But the idea is the same from a solar flare. And you can see this when you get this presentation. You can go to the Hales project at Stanford University. It describes all of this. Next. The GOES satellite. Okay, this is GOES 16. We've had 3 or 4 series of GOES going back to 1990. And so we've tried to align our VLF SID events to these GOES satellites, from GOES 8 to GOES 13 to GOES 15 was the last satellite. And now we're in GOES 16, and they've all create daily data that we use to compare when there's a flare with the VLF data from the disturbed daytime ionosphere. Okay, next. Here's what it looks like for a month. This was May. As Christine says, this was a transition month for us. We had a lot of flares. We had one M-class flare at the very top on the 29th of May. And 2 C-class flares. That was a very active region. 12 B-class flares. And these were recorded by GOES, 16 GOES. So now what we want to do is compare our monthly VLF data with these GOES satellite. So next. When we do the comparison, we look for the length of time that an outburst from the sun impacts the ionosphere. A 2 rating down here in the very bottom is about 33 to 45 minutes. So that large flare on the 29th of May most likely caused a half an hour SID event that in this case was recorded during the nighttime here in Fort Collins, but in Europe, those folks captured the flare. Okay, next. Here's what it looks like during the nighttime for that 29th. You can see how busy. There's a couple things here. Nighttime ionosphere is very diffuse. It's not a mirror. It doesn't become a mirror that we can record city events until the sun comes up and shows ultraviolet light. But you can see the flaring stopped in the most part before 1800, and even a C1 class flare down here in the bottom didn't really make a SID during the daytime here. So it's only during the daytime that we can identify what a SID is, because there's so much noise during the nighttime. Okay, next. I take these data that are given to me a month, and here I make a list of those who contribute. John Wallace looks at NAA, that's in Cutler, Maine. Lionel Laudet, he lives in France, and he captures DHO and GBZ in the Europe community. And Jean-Pierre Godet, he also lives in France. Bob Terrell, he lives in Australia. Frank Adamson is Australia. They look at the Australian NWC. Susan Oatney's here in Canada. Karlovsky's in Ukraine. Rod Green's in Australia. Salvador Aguirre, he lives in Hermosillo, New Mexico, and he captures the Hawaii NPM. And George Silvas there in Massachusetts. Ralph Rogue, who's online, I know, and he's in Germany looking at GQD. And Lou Fiera is in South Africa. So these observers have been contributing data for years. And when this new solar cycle begins, we should see more SID events, not like this one graph here where the daytime is smooth. And we had a nighttime flare. This was in June. Okay, so I used all these data that you might contribute. If you decide to build a radio, or you decide to use sound cards and you're comfortable with Pi Zero computers, email me and I can send you all the details. And that's it for me. We're now going to go to Kim Hay. No, Sarah Beck. Who's next?
So thank you so much, Rodney. It's really cool. And now Sarah Beck is going to tell us how to upload data in the solar database. So Sarah, okay, it's all yours. And while Sarah is uploading her, sharing her screen, I would like to add actually that in addition to the 11 SID observers who submitted observations, we've had more than 100 observers observing a really very quiet sun this past summer. Regardless of the fact that the sun was not doing anything really super exciting or whatever, the data have been extremely valuable because we still need to monitor the minimum in order to actually understand how the cycle works. So this is to express our thanks to all those observers who dedicated their time and energy to observe a really very frustrating object this year. And with that, I'm going to go to Sarah Beck, who's going to tell us about the AAVSO observing sections upload system.
Right. Hello. Thank you, Stella. And thank you all for attending. It's great to see so many people here and so many names I recognize. I'm an employee at the AVSO, and I've been working there for about 30 years, so I know a lot of you. Anyway, I wanted to just start from the beginning to show you like how to start solar observing, how to submit your data, and just a quick overview of what resources are available to you through our website. So probably most of you, if you're not already familiar, this is the homepage of the AVSO website. And the part we're going to focus on is we can either click on this link to the observers landing page, or you can go straight up above our banner there. It says observing sections. So the observer landing page has all kinds of useful information for people that are doing regular variable star observing, or how to get your charts or light curves or whatever. The part we're interested is down near the bottom of this, or lower down the page, where it says observing sections. So there's a close-up of that part, and these are, for those of you who have attended various webinars, you're probably already are familiar with some of these, but the one we're going to focus on now clearly is the solar observing section. So if you click that, you go to, this is the landing page for the solar section. And there's a lot of introduction. It has, you know, how to contact Rodney, Chris, Kim, and lots of good information about the solar section. The other part I'm going to show you now is this blue box over on the right. This has the links to all the pages of interest. So closer look at that. As Chris mentioned, the Solar Observing Guide is where you should start reading, and that's this link. Sun entry, this is what I'm going to be talking about primarily. I'll come back to that in a second. The Solar Bulletin, as Rodney pointed out, that gets published once a month, and it's an online PDF publication. We'll send out an announcement to say it's available, but usually comes around the 15th of the month. And we have lots of years worth of it online too. If you go to that link, you'll see the archives. We have a Solar Observers Forum where you can chat with your fellow observers and exchange ideas, etc., ask questions, and a few other things. And at the bottom here, we have the 3 pages of SID resources, like Rodney was just talking about, the database of flare events from the past, and SID software where you can see all the cool wire diagrams and things from Cap Hosfield. Anyway, so to upload your data, you're going to use a tool called Sun Entry. So if you click that, you go to this page. Now, when you're first starting, you need to, if you don't already have this, you must first create an AVSO website, username and password. This is free of charge. And that will get you, it's very simple, it takes a few minutes, and you get an account. Then you should request an observer code, and this instructions tell you how to get that. Also, that's free and takes a couple seconds. If you are interested in submitting observations, solar observations, then you should send an email to solar@avso.org, which will go to Kim, who you'll meet in a minute, and that just let us know that you're interested in starting to do this, so that we'll look for your observations. Now, Sun Entry is a Java Web Start tool that you need to make sure there's instructions from here on down to the rest of the page that explains how to download. You have to install Java, and then you can click this button to download the Sun Entry software. And there's some other little hints. And if you have any trouble with that, you can contact me, because I am the one that wrote that program. So I can help you sort it out. Okay, now, once you've downloaded Sun Entry, it will, and then you start to run it. It downloads a small little JNLP text file, and you can put it on your desktop or someplace handy. But when you first open it, you're going to get this login. This is the same as the AVSO website login that you just created or already have. So you log in. Now it knows that it's you. So it automatically puts in your observer code. And then the first time through, we would appreciate it if you would fill in this header information. And it's a bit redundant with, other information AVSO might have, but it's going into a different data table. But it also has this information on the right, which tells us a little bit about your instrument and whether you're doing direct observing or projection method, like Chris was talking about, and a few other things about your instrumentation, which might come in handy if we have a special project that we want people with a certain kind of equipment to be able to do. Once you've done this once, it'll save a little the information, and you won't have to do it again unless you change things. So then here's the main SunEntry web page. So it's really, really very simple to upload your data. Once you've made your sunspot observations outside and counted your groups and spots like Chris said, then you can just come in here, come inside, go to your computer, get this open. You can, and you put in the year, month, day, hour, and minute of your observation, and this is in UT. Then you can, this is a little drop-down list of 4 choices for your seeing conditions. So it could be anywhere from excellent to poor. Probably you might not even want to bother if it's poor, but you put in the number of groups, the number of spots, and any comments you might have. Here's an example. And it will automatically calculate the wolf number for you, like Chris pointed out. And then you just click add, and that will put that observation down into this table in the lower part. Now, if you're the kind of person that prefers to collect several days worth of data first before you submit it to the AVSO, you can just do another data point and click add again and have, you could do the whole month in one shot if you want to. Or you can just submit day by day. You can save it to a text file for your own personal use if you like, or the main thing I'm going to say is just click it here to upload it to the database. And that's it. Your data just went into the database. For advanced, once you get some experience, if you'd like to record the north and south hemisphere groups and the central region, which would give a little bit more information, like that butterfly for that butterfly diagram that Chris was talking about, you can, once the record is in this table, you can now modify these fields and put in your north and south groups and central groups. But that's not, you don't have to do that, especially if you're first starting out. Just getting the groups and spots is really what we want most. And then once you've uploaded, once you're ready to go, you hit upload to database down here at the bottom. And a thing should pop up like that. It said, for this session, I've just submitted one record. Now, if you have any question on whether your data actually went into the database, okay, you can go up here to where it says view data. And if you click that, there's 2 menu choices will come up. One is called view archived data, and that will show for any given month that you enter here, it'll show you all the observations that you submitted. I personally am not a solar observer, and these are from my husband, ONJ, who's very keen on it. And then the other option you can do for data, looking at your data, you can get a summary of all your reports in the database if you like. You just go to this little window, hit find, and it'll give you a little summary for each month and year and your total number of observations. So that's kind of pretty much it for uploading data. It's very, very simple. Back to the solar section homepage, one other thing I wanted to point out is, okay, so once you've submitted your data and it goes into our database, there's every month, okay, so Kim will tell you she wants you to submit your data by the 10th of each month, and then Kim and Rodney will compile it and compute the American relative sunspot numbers for each day and each month. And then every month Rodney will send a file that has that information. So we add it, we put it into this link so it gets updated. So if you want data going back to, I think it's in the 40s or so, you can click those things and download a file of data that you can then plot or do whatever you like with it. So this is the output of the data that you have submitted. The other really cool thing that I like is this group LASP. has created a database of all kinds of solar data. They're a group in Boulder, Colorado, I believe. And if you click that link, you can see the AVSO data using their tool. But I think it's just really cool. And you can sit here and use the little scroll bar and zoom in. So this is actually the American Relative Sunspot Number daily version. And you can see all this data coming from AVSO observers that have been combined into one point from all our observers put together. So each point there represents another month, or day, sorry. There's another table they have that has the monthly one as well. But this is how the world, one way in which the world can access the data that you submit. And I just think it's really, it's neat, and they can grab it right out of our database to plot this thing for us. So it gets up to date. It gets updated once a month when we upload the new data. So that's pretty much all I have to say. My pictures actually came from my husband. See, there's a few sunspots here. And if you, on my, where am I? Yeah, so anyway, and you can see up here, that's not a sunspot. And that is the transit of Venus from 2012. But there are a few sunspots in here as well. Anyway, that's all I have to say. Take it away, Stella.
Thank you, Sarah. And last but definitely not least, Kim Hay is going to tell us about how to share sunspot data through the solar bulletin. So Kim, would you share your screen, please? And
Just a minute.
Just 1 minute. Awesome.
How come I don't see it? I'm not seeing it.
We can see it, Kim.
Okay, great. I'll talk to my screen then. Okay, hi, everybody. I'm Kim Hay, and I work with the AVSO Solar Section. And what I end up doing monthly is as you enter your results into the database, for those that do not and cannot for whatever reason, and it's sent electronically, I end up putting it into the database so it's included into the monthly numbers. And we have great conversations back and forth in email with the members who can't submit them, and it's great fun getting to know everybody. So what I basically just want to wrap up this section about is that sharing your sunspot data through the AVSO database. The bulletin itself that we use monthly, published monthly on the 15th of each month, and all observations need to be in by the 10th, so we can put all the data together and get them into the various reports. It's a great source of information from all solar sources around the world, because there's lots of interesting things that happen around the world, and we get to learn about them if you're not online daily or you don't hear about the stories. We highlight solar events and members in the bulletin, and we have the sudden ionospheric disturbance report that has 11 members. I myself, we do have a SID operational. We just haven't collected and put the data in place yet with the GO satellite. So that's what I had sent a note off to Rodney earlier about. I'll be chatting with him later. So I just wanted to say that the relative sunspot numbers, which is submitted by observers. In July, we had 68 observers with an average of 1,374 observations. And this is at solar minimum. So you can imagine what the numbers and the observer numbers will be like once we start getting ramped up into solar cycle 25. Coming up is the Choice Observing and Counting Sunspots course that the AVSO is holding, September 14th to October 9th with Raffaello Braga. It's a very good course. I took it last year, even though I am a, I guess you would say, seasoned solar observer. It is, you can always learn something. So please go to the link in the PowerPoint and sign up for this course because you won't be disappointed. Here's some pictures from member participation. The AVSO solar section does have a solar photo gallery, and some of our members submit pictures to be included either in the bulletin or we have them put online. These two pictures are by Dan Vidican in August this month of when we had the new solar sunspot AR2770. And Monty Leventhal, who actually does sketching. And he sketches the sunspots on his solar disk as well as when he does hydrogen alpha. He also puts it on his disk as well. And he submits this to us monthly. So in wrapping up, you know, read the AVSO Solar Observing Guide for guidance. Go to the web page because there's lots of information. Install Sun Entry. Make sure you have the proper equipment and solar filters in place, or if you're doing projection. And submit your observations and become a citizen scientist in collecting sunspot data. Have fun, it's easy, and be part of Cycle 25 and beyond. And below here, you can see a picture from NOAA and NASA of Cycle 23, Cycle 24, and 25 is still unknown. You never know what might happen. So thank you, and hopefully you will come along for the ride of solar observing.
Wonderful. Kim, thank you very much. So if I might share my screen, let's see. I would like to remind everybody that recording of this and all our webinars will appear on the AVSO's YouTube channel. So please subscribe and go there. And for if you want to listen again, please give us feedback through the survey. You're going to receive a survey at the very end of these webinars. So please let us know what you think and give us some feedback so that we can improve this webinar and others. And if you want to learn more, we're offering a choice course, as Kim mentioned, starting in September. It's a very useful, really very cool way of learning how to observe and count spots. Also, I would like to remind you to renew your membership. Now you can actually renew for 2021 too, and consider supporting the AVSO with a donation. Your donations enable us to bring you programs like this webinar series and provide the support provide and support all the resources that we're providing for our community, including our solar databases, the bulletin, the web pages, et cetera, et cetera. So with that, I would like to transition to questions. We have a very interesting set of questions from our participants. And actually, I would like to start with a general question, and I would like to know the answer actually. How did the ancients see sunspots? Chris?
Well, this is one of those don't try this at home, boys and girls sort of thing. They did it not particularly safely. You know how sometimes when the sun is going down at sunset or coming up at sunrise and there's a bank of clouds and you sort of can see the sun and you don't think it's hurting your eyes and you're looking at it, and you really shouldn't do that, but you can see sunspots if they're large enough, you know, Jupiter sized or larger. You can see them through thin clouds, through smoke. There are some observations done by some ancient Chinese who looked at the reflection of the sun, did not do great things for their eyesight. Do not try this at home. But yes, for the larger sunspot groups, people did actually observe sunspots not quite as safely as they should have.
And actually, if I remember correctly, the whole legend says that Galileo was the first one who measured spots and he looked at them through his telescope, died blind, right? He completely destroyed his vision. That's correct? Do I remember that right?
Yeah, but Galileo took 44 observations in 1610.
Yeah.
And then he changed his telescope because it was hurting his eyes and put a better filter on it. And then he took another 70 observations. So he was pretty familiar with the sunspots.
He was pretty familiar, and he still destroyed his eyes because at least at that time filters were pretty much smoked glasses with smoke. It was nothing sophisticated like the ones that we have here. While we are in the cameras and filters, we have a question that says how to use cameras to measure sunspot activity as an alternative to purely visual methods.
We don't.
Oh.
Yeah, the answer to that is these are visual observations. We can't use CCD computer automated, except for like Dan Vidican, who we can post that he did it. But when you submit your data, there's only one observer who computes the data from the SDO, the Solar Dynamic Observatory, and he uses magnetic images and visual observations. And from that, he can compute the groups from the magnetics and the number of sunspots from the visual. And generally, he's about twice the number of groups and sunspots than the normal observer. So we have to give him a K factor that's 0.5. Because, but that's it as far as CCD imaging goes of the sun.
Okay.
Can I just add? Yeah, it's better. Yeah, what Rodney's saying is that if it'll be biased, if you start using a camera, then you're going to have more resolution, and you'll pick up spots that people can't see with their eyes. So
That's right.
It doesn't work with our, historical data set. So that's why we definitely want visual. And by the same token, I noticed a few people asked about more than one observation per day. No, we only want one observation per day per person. Thank you.
Thank you. Another question, how inconsistent are all the wolf numbers for a single day from all observers? In other words, what is the approximate standard deviation? What causes this deviation? Who wants to answer?
That's why we have Alan Shapley's K factor calculation, because we have 68 observers, and the K factor can go from 0.49 with the SDO all the way up to 1.4. And so we take the average of all the dailies, compute the K factors, and estimate the RA. And then we do that for all daily observations for the month. And then total the K factor for total number of groups, total number of wolf numbers.
So what is the deviation?
And then the R index.
So do we know what the deviation is, or it changes?
Oh, we know it for every day. We don't publish it, but if that becomes a request, we used to publish it before this solar cycle, because it was the computer algorithm that was being used at the time from Grant Foster. So there is historical evidence of the standard deviations from all the people that contributed back in the 90s. We haven't done that, but if that's something that is needed, we can discuss that.
Okay. We have lots of questions coming in. So the general question again, is differential rotation a property of fluids, or is it limited to the stars in general?
Can you
Chris,
repeat
you're
that?
muted.
He's talking, Jupiter undergoes differential rotation, just not to the extreme of the sun, because the rotation of Jupiter is about was it like 10 hours or something? But if you look at the difference between the poles and the equator of Jupiter, there's also a differential rotation. So it's a property of gaseous rotating bodies.
Cool. So still we're speaking about spots. There's a question that says, what is the explanation of the lower peak in the last cycle? I mean, you showed, I think that Kim showed the 2 cycles, right? And cycle 24 seemed to have been much weaker. Do we have an explanation for that, or are we still waiting for 25 to try to get a better picture? Chris?
Well, if you figure that we're on cycle 25, that means we have a data set of 24 data points. And if you have a system that is as variable as the sun, and you've only got 24 data points, of course there's going to be a lot of unanswered questions. And of course your ability to make predictions about the pattern is going to be difficult. If you look at the overall solar data and you stare at it long enough, you can convince yourself that other than just the 11-year period, there appear to be periodicities that last several centuries. And solar astronomers have been debating the cause of that, the reality of that, the robustness of those cycles. There are people who have claimed there have been cycles of about 70 or 80 years, that there are cycles of 200 to 300 years. Going back, even though we don't have sunspot data going back, reliable sunspot data going back beyond Galileo, we can look at aurora data from the Vikings and so forth. And we can use that as a proxy for solar activity. We can also look at the percentage of radioactive carbon-14 in trees and use that, and in ice cores, and use that as a proxy for solar activity. And so there is evidence of cycles, metacycles, that are perhaps in the thousands of years. And again, the question is, how much do we trust all of that, considering that we only have 24 well-observed cycles of the, quote, 11-year cycle? Our data set is just not complete enough, and the sun has enough variability, again, it's a variable star, that we can't really answer.
I find it amazing that the sun is the variable star for which we have data for more than 400 years now, and we still don't understand it. It still surprises us. Just imagine with the rest of the stars, right? Question for Rodney. What would be the recommended receiver for seed observations? The individual says that I've been a ham radio operator for many years. I can work my way through scratch building or kit. Notice the old Drake receiver being used with the app converter. I think I have one or enough pieces to build one of those under the bench. Does this work?
I think the question is, which would be preferable, the old radios with transistors and all, or the new radio with the sound card? If that's the question, it's just a matter of preference. Which would you like? The old radios, generally you can only record one station at a time. With the sound card, over multiple frequencies, you can record all 5 of the American stations or 3 or 4 of the European stations. So it depends on what you like. As far as submitting data to me as for the bulletin, it doesn't matter to me. What we're looking for is those days in which, when the sun shines, you've seen a SID, a sudden ionospheric disturbance. And, it doesn't matter which radio you like, or maybe you want 2 or 3 of the old radios. If you do that, you'll have to have a loop antenna for each of the radios. Whereas if you use the sound card and the Pi software, You only need one loop, one sound card, and one computer. That's cheap and dedicated.
Cool. A
Does
follow-up
that answer
question.
the question?
I think it does, but let me give you another one very similar that says, what is the usual standard for radio transmitter for seed observations, particularly the antenna size and ground elevation? And also, what is the open source software available? Is a typical radio dish type, like the one used for TV, feasible to use as an alternative?
I'm not sure of the question. I guess try to repeat that, Stella, okay?
So the question says, what is the usual standard for radio transmitted for seed observations, particularly the antenna size and ground elevation, and also the open source software available? Is a
Oh, okay,
typical
okay.
radio dish type, like the ones used for TV, feasible to use as an alternative? Can you use your TV dish pretty much for radio? For
No,
radio
not
transmitter?
at these frequencies. You need to build the loop, and there's, if you go to the AVSO webpage and look under SID equipment, there's two types of loops. There's the one using magnetic wire at a 75 centimeter cross. In other words, a small one, and you can put that inside the house. You can have the 1.5 meter with the larger copper wire, and that also can be inside the house. When you put it outside the house, you have weather and deterioration, and you have a longer cable that needs to, generally you can use 50 feet of cable from a loop to the sound card and have no worries. But if you have it outside and it's got 200 feet of cable, then you need to wonder whether or not you need an amplifier, in which case you're back to building a radio. So my suggestion is that you keep the sound card and the loop as close together as you possibly can, and keep it indoors so that it doesn't deteriorate. And if you're, whether the radio's in the basement or whether it's on the second floor, it really doesn't matter. I have mine on the second floor, but sometimes I move it around and it's fine. Now, granted, these are wood houses. These aren't, metal buildings. If you have metal in the wall, that'll act like a Faraday cage and that'll block out everything. So you need to be careful with how close you are to air conditioners. I know Salvador Aguirre there had his on the roof, and he had air conditioners on there and he couldn't receive anything. As soon as he took it off the roof and put it in a place where there weren't any air conditionings or metal, he was able to receive Hawaii fine. So you have to play around. I think Kim's got problems with her metal fence. She tries to put the antenna in the metal fence and it's essentially a Faraday cage. So you have to play around with it because loops are directional. If you're in a mid-latitude and you want to receive the east and west, at least for the United States, then you point your loop east and west, and you can receive Cutler and Jim Creek and Hawaii, and I can even pick up Australia once in a while. But so a lot of these descriptions and tuning of the loops are on the AVSO website.
Thank you. Chris, I think that this is a question for you. The individual says, I'm surprised sunspot counting and classification hasn't been completely taken over by professional automatic systems. Why not? Variable weather?
No, it's again the historical record. And because we have people powered this since the time of Galileo, if we're going to have a consistent record of comparing apples to apples, we want to not bring in oranges. And so we want to make sure that these are really people observing in as similar, the same sort of way, counting groups the same sort of way, so that we can have this consistency, so that we can have confidence that when we check our observations to those of Tommy Craig and those of Tommy Craig back to Wolf, and we have this consistency, so that we can say that we have this record where we can verify that we've been measuring a similar sort of thing, a similar sort of way. And that's what gives true value to the archive and to the records.
So if we are to go back to the basics, what mechanism is thought to generate the sun's magnetic field?
Again, it's the creation of an electric current generates a magnetic field. And so the sloshing around of the electrons within the sun, specifically at that interface region between where the photons are whapping around like pinballs in the radiation zone and the convection zone where the gas is actually circulating, and the top of that circulation zone or convection zone is the photosphere, the visible layer of the sun. But that interface region, that turbulence, if you will, of the electrons are generating an electric current, which generates an electric field. And I'm grossly simplifying, there is a lot about the sun's magnetic field that we do not understand. And part of it is just how the energy goes from the photosphere into the corona and the interplay with the solar flares and the prominences. And there's a diagram that I show my students that I call the scary diagram. And it tries to integrate electromagnetism and thermodynamics and all sorts of other physics to try to explain how energy is transferred in the outer layers of the sun. And it's incredibly complicated, and there's a lot that we don't completely understand.
Speaking of a lot that we don't completely understand, was it coincidental that the Maunder minimum occurred in close proximity to the Little Ice Age?
It's complicated. If you had asked people 20 years ago, you'd probably get a different answer than you get today. As I said, when there are more sunspots, the sun is actually brighter, because when there's more sunspots, there's more faculae, and the faculae more than compensate for the sunspots. There's also more general activity. There's more flares and everything else. And so the Maunder minimum was an extended time, about 70 years, when the sun was very, very quiet. There was also a period of time climatologically where some parts of the world, especially in Europe, where it was cooler. And so the question is that a coincidence or is it a cause and effect? And again, since we understand that a lower sunspot number does mean that the sun would be technically dimmer, people said, oh, that must have been it. But however, historical records have shown in the past decade or so that there was an enhanced amount of volcanic activity, especially in the Northern Hemisphere. And again, when you have increased volcanic activity, there's a lot more ash in the atmosphere that blocks out sunlight, which will tend to cool the climate. So it's a very complicated historical thing.
Yeah. Now, what is the difference between faculae and plages? And do faculae have a similar cycle on sunspots? Whoever has the answer. Chris, we can't hear you.
And Rodney, please jump in. But plages are in the chromosphere, and faculae are in the plages are in the chromosphere, like prominences, and sunspots and faculae are in the photosphere. And so, but all of these things are interrelated. They're all magnetic phenomena, and they're all interrelated in the 11-year cycle. I mean, the solar flare numbers do tend to lag the sunspot number. So it's not like the cycles are identical, like you can't lay them on top of each other exactly, but they're all interrelated because they're all magnetic effects. They're all magnetic activity. Rodney, do you want to add anything to that, or?
Anyone else?
No, I think that's pretty good description. The plage data, plage in French is a beach, and I guess it looked like a beach, so they called it a plage. Those data were captured at the Mount Wilson Observatory for 20 years or so, but now they don't bother much about it. It doesn't seem to be as informative as what they can find from the satellites, like with the magnetograms that Jan Alvested uses to create his, because they have Gaussian magnetic fields on the sun, and they can measure those now. So as we get more and more into the satellites, the magnetic fields become, well, there's magnetic detectors like on GOES and on the SDO satellite. So I think we'll drift with the magnetic fields more in the high tech. For us, to keep the continuity with the Zurich method of classification, we're going to have to stick with groups and sunspots and wolf numbers.
Speaking of magnetic fields, how do you tell the polarity of a sunspot?
Visually, you mean? Of the polarity, or?
Anyway, how can you tell the polarity of a sunspot?
I think Christine described all that with her bipolar. Use the groups. The groups change. I'm beginning to look at data from the Wilcox Observatory in California that talks about the magnetic polarity field and how that switches over, as Christine said, it switches over during the solar minimums. And then when the sunspot flips, once you understand what the polarity is on the poles, the polar fields, then you can track the sunspots because the leader will always be the same from the polar fields for that cycle. And that works until the polar fields flip again. So I think I'm describing that right. Isn't that, Christine?
Yeah, I think what you're talking about is the Zeeman effect. Is just by taking I don't know what it's not a spectrohelioscope. It's, my brain is totally fried. But basically they're measuring they're doing a magnetic field mapping of that sunspot group using the Zeeman effect. And they can actually see what the polarity is. And that way they can tell which of the cycles it belongs to, 24 or 25.
So in principle, just by looking at the sunspots in white light, you can't tell which one is the North or the
right.
South Pole.
Yeah. No, they're not labeled for us. If they had little N's and S's on it, that would just make my day. But unfortunately, no, you have to do the magnetic effects. And if we had magnetic vision, the sun would look so much more incredible.
I know. Stars don't come with labels, do they? We have to figure things out ourselves. Bummer. Well, that's what keeps us interested and employed. So here's another question. What is the current explanation of the increasing temperature of the chromosphere as you go further away from the sun's photosphere? Chris?
Well, I don't think the sun has a troposphere, does it?
Well, I think they mean from the chromosphere to the transition zone up into the corona. Yeah, that's that scary diagram that I show my students trying to figure out the magnetic effects. It is incredibly complicated. It is one of the things about the sun that we really want to know is how that energy is transmitted from the photosphere, which is 6,000 Kelvin, 5,700 Kelvin, to the chromosphere, which is like 3 times, 4 times, 5 times hotter, to, by the time you get to the corona, it's 1.5, 2 million degrees Kelvin. And so we know that it has to do with the detachment and recombining of the magnetic field lines and the transfer of energy in that way, but there's still a lot of details that need to be worked out.
Yeah. Let me give you the last question, which is the million-dollar question in my mind. When did cycle 25 officially begin? It hasn't begun. When will it begin? Cycle 25.
About 6 months ago, they started looking at the polarity change, and then it went back to cycle 24 sunspots, and then that happened for a couple of months, and then it went back to 25. So now it's in transition, and pretty soon we won't see any more 24 sunspots. They'll all be cycle 25.
We're on the tips of the butterfly wings. We're on the tips of the butterfly wings. So getting ready to fly. So join us, because you want to start from the ground up. It's easier to learn how to count spots and groups when there's fewer of them than starting near maximum. You don't want to start trying to learn solar observing near maximum.
Here's another question. Is a seed similar to the ionization impact of a meteor?
A what?
A seed. Is it similar to the ionization impacts of a meteor? You have a meteor hitting the ionosphere. Is that similar to seeds?
Wow. I don't know that I know the answer to that. A meteor coming into the ionosphere burns up because of the velocity of the meteor and the density of the ionosphere. There are amateur radio operators who look at the FM TV channels and then record the reflection of a meteor as it comes into the ionosphere. They're doing a lot of work with that, but it's not got anything to do with us, really.
I think it would be very, very interesting to see the signal that such an impact has and compare it with seed observations. I don't have the answer as well, but hey, something to look up in the future. A general question, I don't have a telescope. What aperture size should I consider?
About 80 millimeters, if you're looking direct. And that means some of the better scopes are from Lunt, or don't get a large telescope. I know Christine showed about a 10-inch SCT telescope, but the problem there is that you have to move the telescope around manually in order to count the spots. You don't want a large aperture. 70 millimeters, 80 millimeters, that's centimeter, 8 centimeters. 10 centimeters is about as large as you want for a direct scope. Yeah, I guess you can go larger if you want to project, but
I've got a 6-inch Schmidt Cassegrain, but I have it on such low magnification. I can see the whole sun in one shebang. But yeah, you definitely do not need a large scope for that.
A similar question. When using a Herschel wedge, there's not always an aperture filter in use, especially on refractors at about 130 millimeters or smaller. What are your comments relative to this filter?
we don't recommend a Herschel wedge. Some people still like that and still do it, and they're very careful about how they do it because it'll just tear your hands apart if you get that. They get very hot. I don't know, Christine. You've thought about that. No, yeah, don't do a Herschel wedge if you're starting, unless you got one sitting there and that's all you got. But we recommend not using one.
And a last question, would a 10 by 50 binocular work with projection methods? Can you project from binoculars? I never tried it.
You don't want to use binoculars.
Oh, you don't want to use binoculars, don't want to observe, but can you project?
It would not be good for your binoculars. They would heat up. It would not be a good thing to do.
Melt.
Yeah.
All you gotta do is buy a cheap old scope for $100, you know, and then put one of those plastic eyepieces on it, and you'll be smelling the burning eyepiece. You gotta read the observation document and all the issues that we discuss in there.
Cool. Well, all the information and more actually resources can be found in the observing section webpage. We have reached at the top of the hour, so I want to be respectful of everybody's time. I would like to thank everybody for being with us today. Thank you to Voice Astro and Attic Cameras who support this webinar. I don't think we would be able to do it without your support. And a heartfelt thank you to our solar section leaders, Chris Larson, Kim Hay, Rodney Ho, and Sarah Beck, for very, very informative presentations and good answers to the questions. Next Saturday, we'll be here talking about cataclysmic variables. So I hope to see you here. So goodbye, everyone, and please stay safe. And thank you for joining us. Bye.
Bye. Thank you.
Bye.
Bye, everybody.